Good afternoon, everyone, and welcome to a live energy analysis aligning budget and energy conservation goals. I'd like to take a moment to introduce your speakers today. My name is Tina Hendricks, and I'm part of the Wildan Outreach team. And today I will also be joined by Ton Dip, who is part of the Wildan Project Management team. So Wildan is a nationally recognized energy efficiency consultant, and we work with the 4 California investor-owned utilities, which are PG&E, Southern California Edison, San Diego Gas and Electric, and SoCal Gas. PG&E does offer several energy incentive programs, including the California Energy Design Assistance Offering, also known as CEDA, which focuses on new construction as well as major renovation projects. This program provides energy modeling services and savings calculations so that customers can get incentives when implementing strategies above and beyond the energy code. And we will also handle all the paperwork for our customers. With CEDA, we strive to make our process as streamlined as possible. We collaborate with the project team early during design, and we hold 2 virtual meetings in order to evaluate the project's scope and energy efficiency goals. That way we can run a whole building energy analysis, which will help the team determine the best strategies for their project, their budget, and their goals. Then once the project is built, the utility provides incentives based on the strategies that were actually implemented. As I mentioned before, today we're presenting a live energy analysis charrette on how to align budget and energy conservation goals. This course is available for credit for AIA members, and certificates of completion are available upon request for both AIA members and non-AIA members. The AIA course description is shown here, which was listed in the promotional materials. And here are the learning objectives for this course. I won't go down the whole list, but essentially at the end of this course, participants will be able to recognize the value of early energy analysis in the design process and how that can increase their energy savings opportunities. All right, listed here is the agenda that we have set out for you today. First, we'll set the stage with some key terms and concepts. Then we'll dive into the energy analysis exercise, in which we'll take a real case study and run a few what-ifs scenarios to evaluate different conservation strategies. After that, we'll reveal the built project results and review key takeaway concepts. And throughout the webinar, we'll be utilizing the polling app to ask you questions from time to time. So let's go ahead and get you set up. You'll need a smartphone, and what we'll have you do is go ahead and text to number 22333, just as you see it on the screen, and type in J Huntsman 632, also shown on the screen, and that'll get you logged in. Then you should receive a text saying that you joined the Jeannie Huntsman session, and that's it. Also, you don't need to click on the polleverywhere.com link that's in the text. In order to start the polls, to send your answers, all you have to do is enter the text A, B, C, or D, just like you would a regular text. And if you want to change your answer at any time during the poll, go ahead and type the word clear, C-L-E-A-R, and that will clear it for you to re-enter your response. Again, A, B, C, D are the responses. Let's go ahead and test the polling app with this question. What superpower would you rather have? A, flight, B, invisibility, C, time travel, or D, crushing deadlines with your fists? So go ahead and text your response now, please. Great, it looks like our polling is up and running. And we'll give it just a second to see if we have a winner.
Tina, we lost the connection. He is back.
Okay.
Okay.
All right. So should I go over the polling again?
Sure.
Okay. So we'll back up, and we're going to be doing some polling throughout the webinar. We'll be utilizing this polling app. if you can go ahead and text into number 22333 and type the word J Huntsman 632, just like you see it on the screen. That'll get you logged in and you can participate in the polling. You'll receive a text saying that you've joined Jeannie Huntsman's session, and that's it. And then you do not need to click on the polleverywhere.com link that's in the text. All you need to do to respond to the questions are simply to answer A, B, C, or D, just as you would a regular text. And if you want to change your answer, you can type the word clear, CLEAR, at any time.
One thing to note, this also doesn't capture or requires a sign in. So none of your information will be captured. Essentially, we're just trying to capture your answers or your responses. Okay.
That's correct. Thanks, Tom. Thanks, Tom. Okay, so it looks like at this point, we have 100% for flight. So I would have voted for that one myself. So A, flight. So we know polling is up and running. So we can go ahead and continue on. Let me begin by asking, how do we get to a clean and cost-effective energy future? So we know that reducing energy consumption of the built environment is vital to success. And as design professionals, we have an important role to play in cutting consumption. Could it be as easy as adding solar to every rooftop? Unfortunately, adding renewable energy generation without first implementing energy conservation measures can have detrimental effects to the grid, which is why we need to exercise our creative problem-solving skills in order to reduce the load of the building as much as possible. All right, time for another poll. And in this poll, we are asking, what types of projects tend to implement more energy efficiency measures? A, residential, B, commercial, C, retail, D, civic, E, institutional, or F, industrial. So if you want to go ahead and text that letter. And this is somewhat of a tricky question, as there are no rules to follow in terms of the types of projects. It very much depends on your building type and what the budget and building owner has. All right, looks like we've got some responses coming in. It looks like 100% towards civic. All right, moving right along. In our discussion today, we'll be talking a lot about EUI, energy use intensity. For those of you that aren't familiar with EUI, it is a key performance metric to understand how buildings use energy. It's measured in kBTUs per square foot per year. You can consider it similar to MPG or miles per gallon in a car, but in this case, you want the lowest number possible. How does EUI work? We take all energy needs in a project, heating, cooling, lighting, anything that makes your meter spin, and we divide that energy consumption by the square footage of the building. By doing so, it normalizes the value independent of the size of the project so that we can compare the efficiency of a smaller building to that of a larger building on a per square foot basis. And the resulting number is the EUI. You might be familiar with the difference between site EUI, which looks specifically at on-site energy consumption, and source EUI, which also takes into account efficiencies in generation and transmission. But for today, we're keeping it simple and we're just looking at on-site EUI. Okay, so now I'm going to hand it over to Tan, who's going to walk us through even further and define other parameters for us. So Tan, where do we start?
So far, we talked about the big picture on the grid and also at the site. Now let's move into energy efficiency in the building. So for example, here are some efficiency measures. And here are some more, and some more, and some more, and some more. And next thing you know, you are overwhelmed to where you can start. So how can you cut through all this and see what makes sense for your project? Well, first, let's build some structure on how we find the right strategies. So let's clean the slate here. The most important thing to start with is always knowing your goals. Is energy cost savings important? Paybacks, EUIs, the LEED, carbon emission reduction, net zero, all these different goals will then lead you down very different paths with your design. So it's important to be first clear on what your goals would be. Now that we identified the goals, it's time to strategize. Well, what strategies do you normally use? Oftentimes, is it rules of thumb, maybe manufacturer's literature, maybe comparing two similar building types to each other. So there's an endless rabbit holes of possibilities that you could turn to. And that's why we have a way for you to get out of that. And it's leveraging the energy models to work for us as a result. So given some methods here, here's another polling. What is the current efficiency measures that you currently use? A, rule of thumb, B, product literature, C, comparison of one project to another, or D, energy modeling. Product literature. Okay. So whenever you're utilizing rules of thumbs, manufacturer's literature, even EYs of other buildings, you need to make sure you're comparing apples to apples. And here we have an example of a pear or an apple asking a pear, are you comparing the orange to me? So let's use an example of a retail center, for example. Same location, same square footage, same window wall ratio, same hours of operations. The only difference between the two is maybe we reorient one by 45 degrees. And you may be surprised that by that reorientation by 45 degrees, that building that's been reoriented will end up consuming a little bit more energy as a result, because let's say the windows are now facing the sun a little bit more. As a result, it demands a higher cooling load during the summer months. So just that one little reorientation may have an effect on the energy load. So as we evaluate your energy models, we're looking for those optimal groups of strategies. We know cost, unless cost is no object, you can't implement every efficient strategy out there. And so when we look at different scenarios, we want to take in consider the cost, the energy savings, and then code. And then we would maybe take a look at 3 different types of scenarios of good, better, best, where good being your current design strategies, better, some improvement strategies upon your current design, and then best, basically, if everything was on the table and cost was not an issue, what would be the most efficient cost-saving measures possible. And when is the best time or greatest opportunity to maximize your energy savings? Well, it's usually as early as possible, usually in schematics and early design development. And the best strategy is always to start with is minimizing the energy load. And then you could start looking into maybe implementing simple cost-effective systems in your HVAC design and lighting. And then applying these measures will minimize your base load and will have less of an impact to the grid. But of course, it's important to remember that at the end of the day, people will operate the buildings a little bit differently than how we may end up predicting it. So when we look at the comparative analysis, we're factoring in some key items here: the building geometry, the square footage, building type, operations and hours, along with the weather. And we're making some assumptions there for average weather, minimum requirements as well. So this could be your HVAC loads, your plug loads, all those go into the requirements. And that's what provides the energy model as a result. And so when we're comparing different energy analysis, what we're essentially doing is basically keeping the geometry the same, the operation the same, but modifying some of those minimum requirements for the project. So maybe changing out some additional energy strategies for those so you can have a proper apples to apples comparison. Now, it's important to remember that combining all of these effects of energy and efficiency strategies is a straight addition. In this case, 2 plus 2 doesn't always equal 4. You know, in this case, it's 3.25. So take, for example, you know, if you implemented LED lighting. Well, LED lighting is great. It generates less energy, but also in turn it generates less heat. So it reduces your cooling loads in the summertime, but in the wintertime, it may end up increasing your winter loads. So that's why we say it's not a straight addition. You need to understand how each one of these strategies interact with each other to give you the overall performance of the building. So it's essentially a comprehensive energy model. So remember that long list of energy efficiency measures we talked about? Well, let's wipe the slate clean here. Let's start with, just narrow it down to 6 categories: building massing, envelope upgrades, lighting controls, HVAC systems, demand controls, and energy recovery. We could add some more, but for this particular scenario, let's focus on these 6. So we actually have an actual case study. This is a project based in Iowa, so it is in the Midwest in climate zone 5. So some of the strategies that we will discuss for this particular case study may not apply for our climate zone in climate zone 3, but I will point out the differences for us as well. So this is an elementary school project. And so we have some basic information for this project, you know, the square footage and typical spaces as well. So here's another polling question here. Now, granted, I'm not providing any additional details or additional context behind this, but what we're looking for is an educated guess for you. So if you can, with your smartphones, pick a particular strategy combination that you think will be the most efficient for this particular project. So is it A, where you would have some envelope upgrades, some daylighting controls, or B, the combination of compact massing, envelope upgrades, and energy recovery, or C, compact massing, geothermal HVAC, and energy recovery, or D, daylighting controls and HVAC command controls. Let's see what your best guess is. C. Okay. Yeah, or D. So we actually have a split right now. So let's go through those 6 efficiency measures, and I'll provide a little bit more context now. So maybe your answer may change now, right? So throughout this process, I want you guys to be aware that we're not going to probably have dollars or costs in here. We're going to kind of use dollar symbols as a way for spending. So imagine we have $12 symbols to spend for efficiency measures, because we know that cost is limited. So we're going to use the dollar symbol. So we have up to $12 to spend for this, and which combinations will work best. Okay, so keep that in mind as we're going through this exercise here. So here we have the first option is building massing. On the left is a base option floor plan. You can see here the square footage is exactly the same for both. The difference between one is the one on the left will have more windows. So that's going to impact your daylighting as a result. So that going with that particular method, even though it's a higher cost as well, may actually reduce the lighting load that you may need. Now, the inverse will happen if you go with the compact form, where you have a reduction in your glazing. But that may also reduce your HVAC load for your cooling load during the summer months. So there's not a right or wrong answer. There is simply cause and effect. And you want to think of these in those particular terms. Okay. Another decision is basically the envelope. Here on the left, we have a basic insulation and basic glazing type. And then the one on the right is an upgrade to that, where we actually have a continuous insulation wall with cutting down on some thermal breaks, thicker insulation on the roof. Pair that where you, let's say, with a reduced solar heat gain glazing type system, will cut down on your cooling loads. Well, something to also keep in mind with the increase in the insulation, that also tends to trap a lot more heat. This particular upgrade may not be beneficial for us in our climate zone because we tend to generate more heat than we do try to trap heat. And that's when you insulate, you tend to trap more heat as a result. So that may have a negative impact for us in our climate zone as well. So, or I wouldn't say negative impact, but a diminishing return. So keep that in mind. That will probably be a major difference for us in our climate zone compared to climate zone 5. The reduced solar heat gain may also have a negative impact on your daylighting as well, because that usually also means you also have reduced visible light transmission for your glazing. So you, as a result, for the higher insulation, you might have to have an increased lighting density for the interior as well to make up for the reduced natural lighting that you would normally have. So there's particular trade-offs that need to be considered when you're deciding on one over the other. Next, we have lighting controls. In the base buildings, we have a standard occupancy and vacancy sensor lighting controls in areas where those types of controls make sense. With the upgrade, we still have the occupancy controls, but we added in the daylighting controls where it will dim or turn off light fixtures when you have enough sunlight into the buildings to meet your need. It isn't super expensive. It's what we call the low-hanging fruit sometimes, but it will help with managing some of those natural daylights or lighting where you already have some natural daylight coming in. Your building massing, usually this ties into what type of building massing you are using as a result too. And here we get into the mechanical. Our base starts with a pretty typical VAV system or variable air volume with a gas boiler, air-cooled chiller. With the upgrade, we're moving into more of a ground source heat pump, also called a geothermal, where it uses a push and pull heat energy in and out of the earth, providing heating and cooling for the building. The geothermal is going to have a higher upfront cost, so keep that in mind compared to the base. This is not commonly, the geothermal is not common for climate zone 3, rarely used in our climate, mainly because we have more of a milder climate than Iowa would have. So as a result, maybe a more efficient system would be for our climate zone would be our VRF heat recovery system over the ground source heat pump instead. Next, we have the HVAC controls. In our base, on the left, we have a typical control system responding to the needs of the various space types on the temperature and maybe humidity. With the upgrade, we're adding in demand controls, which allows us to cut back on the ventilation rates, possibly set back temperature based on whether the spaces are actively being used. These are usually taken into form of carbon dioxide sensors or where they kick in where there's higher occupancy when they determine that's a higher CO2 levels in that particular occupied space. Or a lot of times it's just tied in with your occupancy sensors for your daylighting controls as well. So that's why it's a fairly, once again, low hanging fruit to achieve and very little of a cost impact for to implement. And then last but not least is energy recovery. It's very simply the base design simply do not have it. The upgrade would be including the energy recovery. In this case, we're providing a total heat recovery. So it's basically capturing that sensible and latent heat energy, recapturing that otherwise would be wasted and exhausted out of the building and reclaiming it for other use within the building in itself to make it more efficient. Something to be aware of, it is more efficient to move heat rather than to generate and create heat. So instead of exhausting that heat out of the building, recapturing that heat in and maybe applying that heat to heat up a surface water heater, instead, it's a lot more efficient than exhausting it out. Now that we understand the difference in each strategies, let's see if it changed your mind here. Here, I'm adding in some additional savings ranges, and you can see here with some of these different strategies, there is a negative savings for that, because that's going to vary for the combinations that you would use with each other, or the different combinations of strategies. So given what we talked about here, I'll be curious to see if you changed your mind to see what is now best. Okay, so we see some folks, it was split between, was it C and D, Tina, was it?
Yes, it was C and D before.
Well, now it's B and D.
Okay.
So, all right. So let's take a look at how we did here. So let's look at the results that you guys chose. Because it's split, which one should we go with, Tina? Seeing how it's split, B or D?
Let's go with B.
Let's go with B. Okay. So with B,
We've
you
got the massing.
compact massing, was it?
Yes, yes,
Okay. And then the envelope was upgraded.
yes.
And then daylighting controls was
None.
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 Okay.
And then energy recovery.
B. Okay, so B was just a standard VAV system, right? No
Correct.
demand control, and then they decided on energy recovery. Okay.
Correct.
Good to know. All right, let's see the results here. So, wow, you guys chose the most efficient strategy possible. So here we have an example of all those 6 combinations, and we totaled up to 32 types of combinations available. So the EUI is a 40.2, and the total energy savings, annual energy savings available is now close to $65,000 a year, with a reduction of 34% peak savings. So that is the most efficient strategies out of the combinations ranked. And you could see here, out of those, we are number 1. So that is the most efficient. So let's go further here on these combinations and the variety of the combinations and how they relate with each other here. So I made mention of those 32 possibilities. So the lowest is close to, or the base design is close to $23,000 energy savings. And the highest is 65. So you can see here, we have a 40% chance with a number of 31 combinations to reduce energy. And as we talk about some of these different strategies, you could see here the dispersed form strategy is included in 2 of the lowest energy savings designs. But it is also included in some of the higher savings design groups or combinations. The saving that you see here are very heavily tied to which mechanical system you decide to implement the heat loss. As I mentioned before, the design strategies are not a straight addition. It is, it's not always 2 + 2 = 4. It's dependent upon those combinations you use with each other of those design strategies. And that's why you can see here for the dispersed form, those are all over the board. When we take a look at the ground source heat pump savings, they're a little bit surprising here. You would think that it would actually be, a lot of it would be more on the higher tier, but you can see here, it's more falling in the middle of the group. And this is mainly because the cost of natural gas is relatively cheap right now. And this option switches from natural gas to electric heating, If the cost of natural gas went up, the cost of electricity went down, this grouping would change. Now, this is mainly energy cost savings, and we're not looking at really the energy use intensity. If this was based on energy use intensity, this would actually be on the higher tiers. Okay. And then the HVAC demand controls are included in the groups all across the board here. So it leads us to believe that this isn't a huge driver of energy savings, and it's really going to be dependent upon the combination of the demand controls you use in combinations with, either your compact massing, your building envelope, or even your mechanical system as well, or even in combinations with the energy recovery. But when we talk about energy recovery, you can see here that's in the top 9 on this board. So you can see how big of an impact an energy recovery combination really has onto the efficiency of the building in itself. It's mainly because, once again, this is in Iowa, very cold winter. I may mention it's more efficient to move heat rather than generate heat. So recapturing that wasted heat back into the building for other use really makes the building much more efficient as a result. And then the envelope upgrades, it's important to see that although it's very expensive, it is across the board, and it's really dependent upon the additional strategies that you do combine it with. And you can see here, the highest improvement, or the top tier, is having that upgraded efficiency or envelope with an energy recovery system as well. And like the demand controls for the ventilation, lighting controls are all over the place. So once again, it tells us it's not a big driver for energy savings, and it's really dependent upon how you combine that with the energy, with additional energy strategies. That's going to give you your most beneficial energy efficiency as well. Once again, your daylight and HVAC demand control combinations are what we call the low-hanging fruit. Pretty easy to implement, and very little incremental cost for the project as well. Now, a lot of times, a lot of folks think, well, in order for me to be efficient, I have to spend a lot more money. Not necessarily the case here. You can see here, we have listed all the lowest cost combinations available. And you can see here that 1, 2, 3, 4, 5, the 5th, there is a low cost option for that. And I believe that is including in this particular strategy, the energy recovery system. So let's go through the built project results. The optimal time to maximize savings on the building, as I said before, is early in design or early in schematic designs. And you always want to try to minimize the energy load, followed by implementation of a cost-effective system. But of course, by the time the building becomes occupied, it's key to remember that the occupants can easily use the building a little bit differently than what was predicted in design. So what was actually built, or the team decided on? Well, they decided on actually D, the low-hanging fruits. So essentially, they went with the dispersed form design, a basic envelope, daylighting controls, the VAV HVAC system, demand controls, and no energy recovery. The reason why they decided against the energy recovery was maintenance. The maintenance department was not too familiar with maintaining it, and so they didn't feel comfortable in implementing it immediately. So here's where the project ended up being. You can see here, although we chose B and the most efficient measure, They ended up going with something that instead of being ranked number 1 out of all 32 combinations, they went with something that was ranked 30 or 27th. So they have an annual energy savings of close to $34,000 a year with an EUI of 61 and a peak energy savings of 31%. Something to be aware of, actually, when they were going through the process of construction, the facility director actually decided to move away from the VAV system, and they actually decided to implement the geothermal. So actually, and the reason why it took them a little bit long to make that decision was because they needed to learn a little bit more on that geothermal system and get comfortable with it prior. Once when they did, they decided to pull the trigger, and they ended up spending a little bit more additional funds for that. And it ended up exceeding their budget, but because they implemented that, that actually moved the needle a little bit further. So they actually jumped up. They actually now have an energy cost savings of closer to $43,000 a year. So it's probably closer to 14th, 15th places where they're running at right now. And here we show where they are consuming, and this is in green, but the downfall is what we predicted was actually much lower. So the peak, they're actually consuming about 10% more than anticipated. Now, the reason being is, if you can see here, the biggest consumption or peaks were during the summer months. Well, found out during, a chance for us after construction was complete, and basically had a chance to go through their meter data to see what is actually being used. We found out that they were using the facilities a lot more frequently than they did anticipate during design during the summer months, because seeing how it was a new building, the community liked having the fresh new building. They ended up having a lot more events during the summer months inside the new building because of that. And so that increased the additional energy demand because of that. The other factor that increased the energy demand or usage was the fact that they ended up disabling the daylighting controls, mainly because one school teacher complained about the lights not working correctly. So instead of trying to fix the problem, they ended up just turning off the controls and ended up basically rendering the daylighting controls useless. So they were as running efficiently as they would have predicted they would have. So as a result, once when they found that out, they recalibrated the controls and started implementing the controls again to help reduce some of those energy consumptions. So if you learned anything from the energy use from this project here, energy use has changed, so it's nothing to panic over. So if energy use has changed, perhaps, going back, trying to understand, well, has the hours of use have changed? Has the space been used, or the function has changed a little bit and how it's going to be used? Maybe the anticipation of higher plug loads wasn't anticipated, or controls have been overridden in this case with the project that you could see that I made mention before, that they overrode the controls, or maybe, which rarely happens, in equipment malfunctions. So it's good to not only once when you have your energy models and designed and you completed your project, to also make sure you have some levels of benchmarking and a way to verify and measure how the building is performing, and verifying that it is being used to the design that it was intended for. So in drawing to a close, some key takeaways in evaluating project's energy potential. With every project being different, it's important to establish those energy goals early in design, especially when utilizing model data to support your design decisions. Partnering with your electric providers to help take advantage of any energy consulting services. And of course, it's key to remember that people running these buildings differently than what may be anticipated. And to quote Donald Watson, who's a fellow AIA, who was actually a committee member for the AIA Energy Committee in 1973 by Jimmy Carter, he is quoted as saying, energy is a design topic, not a technology topic. So with that, that concludes our presentation. This is my contact along with Tina's as well. So with that, thank you so much for having us. Our contact's up above, and feel free to reach out if you have any additional questions.
Thank you, Tom. And thank you to the AIA as well, East Bay.
Thank you both. This was a great presentation.
Great. Thank you so much.
Thank you. Bye.
Bye.